Okay, guys, welcome to Chapter 12. Chapter 12 is a whole chapter on what's called stoichiometry. Stoichiometry is going to basically take what we learned about the mole map, going from moles to atoms or from grams to moles. It's going to take it one step further and relate this to chemical equations, what we did last chapter. Now, stoichiometry, by definition, is the calculations of chemical quantities in a chemical equation. This is an important definition. You must be able to do the following in order to solve stoichiometry problems. You need to know your nomenclature. Okay? You need to have some idea about predicting products from the types of reactions, but you won't really need to rely on this part too much. You will need to know how to balance chemical equations. You will need to recognize significant figures, and you will need to use the concept of the mole map, understand how to use it, and how to use unit conversions. Now, we are going to be moving somewhat rapidly because there's not all that much material to cover in this unit. All right, once you get the concepts down, the concepts will be applied over and over and over, and all we're doing is a series of unit conversions. So if you have good unit conversions, you're going to be able to understand stoichiometry quite easily, as long as you understand the mole map.
Chocolate.
So we want to look at chocolate chip cookies in order to help us understand stoichiometry. So here is a standard recipe for chocolate chip cookies. While I'm using chocolate chip cookies as an example, I'm not condoning the consumption of chocolate chip cookies. So if we wanted to look at this recipe, and we wanted to look at how many eggs are going to be needed to make 3 dozen cookies. Well, we can easily set up a unit multiplier to figure out that in 3 dozen cookies, and we want to go to eggs, we know that this recipe is for 3 dozen, 2 eggs per 3 dozen. Dozen cancel, 3 cancels, so we need 2 eggs to make 3 dozen cookies. How much butter is needed for the amount of chocolate chips used? All right. So we once again look back to our recipe to see how much butter is needed for the amount of chocolate chips used. And we see that we need 1 cup of butter per 2 cups of chocolate chips. Now, what if we wanted to look at how many eggs would be needed in order to make 9 dozen cookies? Well, all we would do then is we would go back and take our unit multiplier, and instead of starting with 3, we start with 9 dozen. We know that 2 eggs per 3 dozen, and we'd multiply 9 times 2, which would give us 18, divided by 3, which would give us 6 eggs. All we're doing is creating unit multipliers based upon our recipe that is listed. And what I want you to do now is calculate how much brown sugar would you need if you had 1.5 cups of white sugar. 1.5 cups white sugar. So you should have that in your notes. Well, what do cookies and chemistry have to do with one another? Well, just like chocolate chip cookies have recipes, chemists have recipes as well. And instead of calling them recipes, we call them reaction equations. And instead of using cups and teaspoons, we use moles. And since we can't measure things exactly in moles, we measure things in grams, then convert them to moles, and then we can do our recipe based upon our mole conversions. And the last thing, instead of using eggs, butter, and sugar, we use chemical compounds as our ingredients. So by looking at a reaction, we know something about the product and how much product we're going to be expected to get, just like a cookie recipe. So the first thing you're always going to need to do is you're going to always need to have a balanced chemical reaction in order to start. In this example, we see that the coefficient 2 tells us that if we mix 2 moles, all right, because these coefficients are mole ratios, if we mix 2 moles with 1 mole of Cl2, we're going to get 2 moles of sodium chloride. If we wanted 4 moles of sodium chloride, all right, we would need to double our recipe. We would need 4 moles of sodium and 2 moles of Cl2. If we wanted 10 moles of sodium chloride, well, we'd have to set up some unit multipliers to figure out the number of moles required of our products, of our reactants, in order to get 10 moles of product. Same with 50 moles. So we're going to use the mole map, and for this unit, we're going to focus first on this portion, and second on that portion. Now, we already know how to do this portion. In green, this is our previous knowledge. But if you notice, here, here, or here, we do not need Avogadro's number. So do not just throw Avogadro's number in blindly. So let's practice. The first thing we're going to practice is we're going to look at a balanced reaction for hydrogen gas reacting with oxygen gas. Hydrogen gas reacts with oxygen gas to form water. In this reaction, we have 2 moles of hydrogen reacting with 1 mole of oxygen to give us 2 moles of water. How many moles of reactants are needed? What if we wanted 4 moles of water? What if we had 3 moles of oxygen? How much hydrogen would we need to react, and how much water would we get? Well, what we need to do is look back at our chemical equation. So how many moles of reactants are needed? Well, we have 2 moles of hydrogen, 1 mole of oxygen. We need 3 moles of reactants. If we wanted 4 moles of water, we easily can just see if we need 4 moles of water, we're doubling 2, so we would need to double the amount of our ingredients. So if we wanted 4 moles of water, we would need 6 moles of reactants, 4 hydrogen, and 2 oxygen. If we had 3 moles of oxygen, how much hydrogen would we need to react? And how much water would we get? Well, if we tripled the amount of oxygen, we would need to triple the amount of hydrogen. So you would need 6 moles of hydrogen, and we would get triple the amount of water. We'd end up with 6 moles H2O. Now, we're just doing easy ratios in our heads for this, but let's look at a little bit more complex practice problem. Before break, you witnessed the combustion of ethanol. If 0.250 moles of ethanol were burned, how many moles of water are produced? The first thing we're going to need is a balanced chemical equation. So the formula for ethanol is that. It's a combustion reaction, so it reacts with oxygen. And our products are now what we don't have here is a, oops, made a mistake there, guys. That's H2O. We don't have a balanced chemical equation. So we're going to first need to balance our equation. On the left side of the reaction, we have 2 carbons, 3, 4, 5, 6 hydrogens, and 2 oxygens. And we have 1, 2, and 3. So we're going to put a 2 here to give us 2 carbons, but that gives us 4 and 5 oxygens. We're going to put a 3 here. This gives us 6 hydrogens, and it gives us 3 and 4, 7 oxygens. We have 1 oxygen here, so we have 6 to account for. If we put a 3 here, that gives us 6 plus 1, 7 oxygens. So we now have a balanced chemical equation. And we're going to plan our route using the mole map. And the mole map we're going to use, we're starting at moles of ethanol, and we want to know how many moles of water were burned or were produced. So our starting point is 0.250 moles of ethanol. Our end point is moles water. We're going to set up our unit multiplier with just words first before we put any numbers. So we were leaving moles of ethanol, so moles of ethanol will be on the bottom. We're going to moles of H2O, so moles of H2O will be on top. And then what we're going to do here is it says the balanced chemical equation is going to help us with our unit multiplier. So we're going to take the coefficients from the balanced chemical equation and put them next to the terms. So we have 3 moles H2O, 1 mole ethanol. 0.250 times 3 is 0.750. Our sig figs, whatever number we start with for sig figs, is going to be the number of sig figs we end with. So our answer here is 0.750 moles of H2O. This might seem confusing at first. Put this in your notes, put the practice problems, and we'll do a lot of practice tomorrow in class.